Hello, welcome to MAT 307 Numerical Analysis class. In this lecture, we'll talk about machine numbers, computer arithmetics, and errors. First, what is numerical analysis? Numerical analysis is concerned with solving problems numerically, developing a sequence of numerical computations to obtain a satisfactory result. A significant part of this process is to figure out the errors that arise in these computations. These errors are due to arithmetic operations or other sources. Okay, so the numerical analysis will be dealing with solving problems numerically, and it will measure the errors that might arise due to these computations. So first, let's start with a definition, decimal floating point representation, because we all talk about machine numbers, and this will be an introduction for that. So let's consider a non-zero number in decimal system. Then this number can be represented uniquely by this form. Here the number S is the number we want to represent. The sigma is the sign of the number, either positive or negative. So D is the mantissa or significant, and N is the integer exponent. Okay, so this D has to be between 1 and 10, and 1 is included, 10 is not. So this number will be either 1 point something or 2 point something, 9 point something, like that, but not 10 point any number. Okay, so this has to be between 1 and 10, 1 is included. So an example will be 126.329. So for this number, the mantissa has to be between 1 and 10. So we need to write mantissa as 1.26329. So this means we divide the number by 10 to write it in this form. So for not 10, 100. So for compensation of this division, we need to multiply by 100 to move this point to the right to decimal places. Okay, so for this unique representation, we see the sigma, the sign of the number is positive, so we have positive 1. The exponent is 2, and the mantissa will be 126.329. Okay, so let's also consider this number. For this number, we need to again divide by 100, so we need to write the exponent as 10 to the 2, and the sign is negative, so the sigma will be -1, the exponent will be 2, and the mantissa will be 7.26329. Okay, computers use binary arithmetic instead of decimal arithmetic. So the representing each number as a binary number means a finite sum of integer powers of 2. Okay, so we need to write a number as a finite sum of integer powers of 2, and then represent this on the machine in a computer. Okay, so this representation has to be finite because the storage in machines are limited, so we cannot write infinitely many numbers there. We cannot represent infinitely many numbers there. This sum has to be finite. So for this reason, some numbers can be represented on the machine exactly, but some others cannot. Okay, so for example, if we consider this number 5.25, the binary number representation of this number will be 2 to the second plus 2 to the 0 plus 2 to the -2 power. So this will be basically 4 plus 1 plus 1 plus 1 over 4, so 0.25. This will be 5.25, which is here. Okay, so this number has an exact representation in finite binary system because this is a finite sum of integer powers of 2. But in this particular case, 1/3 will be written as 2 to the -2 plus 2 to the -4 plus 2 to the -6 plus 2 to the -8. It continues like that. So for this particular number, the sum is not finite, so this number cannot be exactly represented on a machine. Okay, so a floating point number, the way a real number represented in computers, approximates the real number. For example, for this case, it is exact, but for this one, it has to be an approximation to the real number 1/3. Okay, so definition for binary floating point representation. Let's consider the number s, non-zero number s in the binary system. Then it can be uniquely represented as s is equal to sigma times d times 2 to the n. So the sigma will be the sign of the number. This d will be the significant or the mantissa. So for this particular case, the mantissa has to be between 1 and 2. 1 is included, 2 is not. So this can be any number like 1 point something, okay? Nothing else, 1 point something. So this 1 is there for sure. And the number n is an integer, and it is standing for the exponent. Okay, so an example for this representation will be this number. Okay, so we need to move the dot to the left to this position. So this means 1, 2, 3, 4 times moving the dot to the left. So this means we have 2 to the 4 power, and then the mantissa will be 1 point other number. Okay, so the sigma will be positive 1 because the sign of this number is positive. The exponent will be 4. If you want to represent this 4 in the binary system as well, this has to be 1, 0, 0, because if you convert this to a decimal number, this will be 0 times 1, 0 times 2, and 1 times 4. So 1 times 4 will be basically 4. And the mantissa will be this number we see here. Okay, so this is an example. Another example will be this number. So we have negative, so the sign will be -1. Okay, the exponent is -2 because we move the dot to the right 2 places, so this will correspond to the -2 power. Okay, so if we will write this in the binary system as well, then we will have -2 will be equal to -1, 0 in binary system, because again this is 0 times 1, 1 times 2, so 1 times 2 will be 2 basically, with a negative sign will be -2, and the mantissa will be this quantity here. Okay, so in machine numbers, machine floating point representations, there are some standards. The one standard is given here. This standard is pretty much all the computers, what the standard that pretty much all the computers use. In this standard, there are two basic representations of numbers. So one is single precision with 32 bits, and the second will be double precision with 64 bits. This is not the only option, but this is a standard our computers use. If you want to build a machine with, for example, 8 bits, that's also possible. Or maybe if you need better computations, you might build a machine with 128 bits. This is all up to you. But if you want to use the standard, this is here. Okay. So for this standard, we have 32 bits. So we can represent 32 numbers. For the first one, the first number will be allocated for the sign of the number. The next 8 will be representing the exponent of the number, and 23 will be the mantissa. In the double precision, the first one will be the sign, 11 for the exponent, and the next 52 will be the mantissa. Okay, so this is what we have in standard form, in IEEE floating point arithmetic standard. Okay, so single precision floating point representation of S has a precision of 24 binary digits in mantissa, because in the binary system, this was in the unique representation, this was always 1, and we have 23 numbers allocated for the mantissa. This will be an extra 1, and which is an elegant way to construct the numbers. Then this means we have 23 plus 1, 24 digits for the mantissa, and the exponent will be exponent. In the exponent, we have the limits like negative 126 to 127, because we have 11 positions for the exponent. This will only allow us to store exponents in this interval. Okay, and sigma will be basically either 0 or 1, and we have two options here. Okay, so the exponent fields needs to represent both positive and negative exponents, because in the previous example, like here, we had negative exponent here and positive exponent there. Okay, so this means the exponent can be either positive or negative. Okay, so the exponents in the interval from 0 to 126 have negative sign, and those in 128 to 255 will have a positive sign. Okay, so we have basically 256 options, and we reserve the first half of these options for negative signs and the other half for the positive sign. So this means a bias 127 is added to the actual exponent in order to get the stored exponent. Okay, so the exponent will be always positive. So the stored exponent will be always positive. So in order to see the actual exponent, we need to subtract 127 from the stored exponent to obtain the actual exponent. Okay, so letting k be the number of reserved bits for the exponent, then the bias given here can be found with this formula. So 2 to the k minus 1 minus 1. Okay, so in this in the single precision case, this will be 2 to the 8 minus 1. So this will be 2 to the 7 minus 1. So 2 to the 7 will be 128 minus 1. This will be 127, which is given here already. This is the way we find the bias. Okay, so say the stored exponent in the machine is, for example, 130. Then the actual exponent will be 130 minus 127, which is 3. Okay, so this means the exponent 3 is represented in the machine as 130. Okay, also the exponents 0 in all positions, so this is 8 zeros in binary system. This is basically 0, and 8 ones in the the exponent position. This will be 255, and these two numbers are reserved for special characters like plus and minus 0, plus and minus infinity, and not a number. Because if you see our assumption, s was non-zero, but 0 is still a number, so we need to represent 0 in the machine as well. So this means we have reserved some numbers, some exponents, the very first exponent and the last exponent, for this special characters like 0 and positive, negative, infinity, and not a number. Okay, there are some other special characters as well, but these are the most commonly used. Okay, so for this reason, the greatest and least positive floating point representations are given in the table like that. So say we are dealing with the positive floating number and least positive floating number, and the greatest floating point number. So the greatest will be then 0 in the sign, because we are working with positive. So 0 will be the sign, and in the exponent this will be ones all the way up to the last position, and in the last position we have to have 0 instead of 1, because if we put 1 here, then it won't be a number but a special character. Okay, so to make it a number, we need to replace this 1 with some number 0. Okay, so this way this will be a number, not a special character. Then in the mantissa we can have ones everywhere, so this number will be in the decimal system look like this number. Okay, so the greatest positive number in the machine will be 3.4 times e to the 38. Okay, so this is for the single precision. Okay, what about the least positive floating point? So we still have 0 because we have positive numbers, and least number can be obtained by having the least exponent. So for having least exponent, we have to have zeros everywhere, but zeros everywhere is a special character, so we need to replace the last position with 1. This way we can obtain a number instead of special character. And for the mantissa, we have to have zeros everywhere to have the least number. So for the mantissa, this will be 1.0, and from the exponent, this will be basically this is 1. If you subtract this from 127, I mean subtract 127 from 1, this will be negative 126. So 2 to the negative 126 will be pretty much this number, so approximately this number. So this will be the least positive floating point on the machine. Okay, so let's talk a little bit more about here. So this means the least positive floating point is defined on machine numbers. In reality, if we have two real numbers, there is always one real number in between. Okay, so given 2 points in the real line, we have infinitely many numbers in between these two numbers. Okay, but in the machine, since we have infinitely many numbers, there is gaps between numbers. Okay, so the gap between 0 and the next number will be this much. So this is the very first number after 0. Okay, let's see some examples. First, the number 1 can be represented on a machine like that in a single precision. So it will be basically a 0 in the first position because it's positive, and the exponent will be 127, and the representation of 127 in the binary system, because 127 is the bias, and we have to have 2 to the 0 power, so 127 has to be the exponent for this number to make it 0 on the power of 2. And also mantissa will be all zeros, and we know hidden 1 is there, so 1.0, so the mantissa will be 1, and the exponent will be 0. Basically 2 to the 0 will make it 1, so 1 times 1 will be just 1. Okay, let's also consider number -2. So for this number, we have this representation. First, the number is negative, so we have 1 instead of 0 in the first position, and this will give us negative. And then in the exponent, this in the 8th place, we have 1, so this will be 2 to the 8. 2 to the 8 is 128. If you subtract 127 from the bias, this means we have 2 to the first power. -1 times 2 will give us -2. Okay, so let's also consider this number, and the last one will be for you to practice. Okay, so in this one we have a positive number, so the first first digit in the binary number will be 0 to make it positive, and in the exponent we have this quantity, okay, and minus 127 for the bias, and this quantity will be basically 0 times 1, 1 times 2 to the power first, power 1, and then here we have 0 times 2 squared, and here we have 1 times 2 cube, so it's here 1 times 2 to the fourth, here 0 1 2 3 4, okay, 1 times 2 to the fifth, and 1 times 2 to the sixth, and nothing else. So these are the binary representation of this number, minus 127 from the bias, and we have -5, the actual exponent of the number, and the mantissa is 0 0 1 and all zeros then. So this will be like this number in decimal system plus 1, because we have hidden 1 here and the in the mantissa. So this will be basically 1 plus this is 2 to the -1, 2 to the -2, 2 to the -3, which is here. So this will be 2 to the -3 plus 1. So this will be basically 1.125. Okay, so the number, the real number, this number, positive 1.125 times 2 to the -5 is basically equal to this quantity, and this number represented on a machine like that. Okay, so the last one will be your for your practice. Please do it on your own. Okay, errors and computer arithmetics. Infinitely many real numbers are represented by finitely many floating points in a computer, just like I told you before. So we have infinitely many numbers in reality, but finitely many floating points in a computer. Let's say a number S has a mantissa D is equal to 1.A1, A2, that's AN minus 1, AN, and AN plus 1. But the floating point representation may contain only n binary digits. Okay, so say our mantissa is limited by n bits. Okay, then it means we can only represent the number as much as this length. Okay, so the last one will disappear somehow. Okay, then s must be shortened when stored. The definition gives us how the ways to shorten this number. So we denote the machine floating point representation of s by FLS. This is standing for floating point. FLS. We either truncate or chop D to n binary digits. So this means we ignore this part basically. AN plus 1 will be dropped, and then we will obtain a shortened version of this number and then store this number instead. Okay, or the rounding will be the number, say round D to n binary digits. Okay, so to the nth position. Okay, nth position. Then based on the size of the following the digit n. So based off the size of this number. Okay, so an plus 1. If this an plus 1, the n plus first digit is 0, then chop d to n digits. Okay, ignore this part and basically store the number up to an. Okay, if n plus first digit is 1, then chop d to n digits again, but add 1 to the last digit of the result. So add 1 to the an. Okay, so this is rounding. Okay, it can be shown that floating point representation of s is equal to s times 1 plus epsilon. Okay, so this is there will be a small number s, and s will be represented as this way. Okay, so if the chopping is used, then this epsilon, the error will be between negative 2 to the negative n plus 1 to 0. So this is a bound for error. And if the rounding used, we have a bound for the error like that. Okay. So due to chopping, the worst possible error, which is here, the worst possible error might be this quantity. This number is twice as large as when we round the number. Okay, so this error is 2 times that error. Okay, so this means the chopping introduces twice as large error when comparing to the rounding of the number. Okay, in the worst case scenario, of course, the sign of the error in this in the chopping will be always positive. Okay, always positive, because sorry, always negative, sorry. So it means we have always negative number, so the error will accumulate. Okay, there is no way errors cancel. Okay, let's see what happens when we round numbers. The worst possible error, which is either this one or that one, is the half of the chopping. Okay, the error of chopping. So this is quite well. And also the error s minus floating point representation of s is either negative or positive. In some cases it's positive, or in the others it's negative. So this means if we apply operations, if we do operations with these numbers, there is a better chance to cancel this error. Say in one number the error will be positive, in the other number the error will be negative. So if they add it, then these errors might cancel. But in the chopping case, it's always negative, so there's no way they can cancel. They will accumulate or propagate much worse. Okay, so the error propagation behavior of rounding will be better. Okay, so the error in an approximated quantity is defined as error SA. The SA is the approximated quantity. This is S true value of S minus SA, and this is called as the absolute error. Okay, so the absolute error will be given by the absolute value of the difference between the true value minus the approximated value. Okay, the relative error is another way of measuring error. So this is error divided by the true value. Okay, the absolute error divided by the true value. So we take the difference between the true value minus the approximated value and divide this by the true value, and we will have the relative error. The notion of relative error is more in strict error measure, because say the exact distance between two cities are, say, 100 kilometers, and the measured distance is 99 kilometers. Then the absolute error will be 1 kilometer, and the relative error will be 1%. Okay, 1 kilometer in 100 kilometers. Okay, so the exact distance between two cities, say in another example, 2 kilometers, and the measured distance is 1 kilometer instead. Okay, in this particular case we still have 1 kilometer absolute error, but in this case we have relative error is 50%. Okay, so the error is quite high if we consider the relative error, but absolute errors are the same for these two examples. Okay, so sometimes if you're working with big quantities, relative errors are more strict. But if you're working with small numbers, the small numbers themselves has some issues with cancellation sort of thing. So we prefer the absolute errors when we are working with small numbers. So these are two different errors, and we use what we really need, and we need to represent. Okay, so there are two options. These are two options. Okay, so if we are doing computer arithmetic, say we are taking the product of two numbers. When doing calculations with numbers that contain an error, the result will be affected by these errors because the numbers themselves are not exact already. So the product of these two numbers will not be exact as well. So this phenomenon is called the propagation of error. The example, for an example, let's say x is given this way: floating point representation of x plus some error plus and y is equal to floating point representation of y plus some error with y. If we take the product x times y minus floating point representation of x times y divided by the absolute value of x times y, this is the relative error. And this will be basically if we substitute x and y values from here, from this line, then we will have x times y minus x times e to the x times y times e to the y. Okay. Then if we distribute these two numbers, then we will have y times e to the x plus x times e to the y plus e to error. No, it's not e to the x. Error x and error y, and this will be error x and error y. So the error x times error y is expected to be small comparing to these quantities because error will be small number, small positive number, and if you take the product of these two, this will be comparing these two quantities will be very small, so we can ignore this number basically, and then we will end up with these quantities. Okay, so the relative error will be, then the relative error is given with this formula, and this will be basically e to the x divided by x because these y's will cancel out, and plus e to the y divided by y because x's will cancel out, and we will end up with this. This is basically the relative error for representation of x, and this is the relative error for y. So the relative error with the product of two numbers, the relative error of x times y will be basically equal to the relative error of x plus relative error of y. So this is the propagation of error. Say the relative error with x is some number, and the relative error for y will be another number, and the error will accumulate, and this will propagate when we apply operations on these numbers. Okay, the stability. Some numerical methods may tolerate small fluctuations, errors in the input data, or due to the computation itself. Okay, some methods can tolerate small fluctuations, but others might magnify them to deviate the computed solution from the exact solution exponential effect. Okay, so this is basically, there are some numerical methods that can tolerate small errors, small fluctuations of errors, but some other methods cannot tolerate uh, the small errors, and it will deviate from the exact solution exponential effect. Okay, so calculations that can be proven not to magnify approximation errors are called numerically stable. If this method do not uh, disturb themselves too much from small fluctuations, then we call this methods numerically stable. And if they are disturbed and they diverge from the from the exact solution, then we say that these methods are unstable or unstable. Okay, so an example, finding the root of this basic quadratic equation, we use the quadratic formula. The x1 will be negative b plus the square root of delta over 2a, and x2 will be the negative delta of this. Okay, this is unstable if b squared is much greater than the 4ac, the absolute value of 4ac. If b is less than 0, say, the cancellation occurs in x2, since negative b is approximately equal to the square root of b squared minus 4ac, because 4ac is very small comparing to b squared. Okay, so this means this will be in the x2, this will be basically equal to negative b, and this being negative b, we will have x2 is approximating to 0, even if it does not. For this particular case, if b is greater than 0, then the cancellation occurs in x1, because in this particular case, b will be very close to the square root of delta. Then this will be basically equal to b, negative b plus b will be 0, or approximating to 0. And this will cause issues when we have basically b squared is much greater than absolute value of 4ac. In both cases, b may be exact, but the square root introduces errors. So for this particular example, we say this method is unstable if this condition is satisfied. Okay, so that's all for today. Thanks for watching. If you have any questions, please feel free to contact me. Bye.